quantum communication and QKD. My name is Panagiotis Vergyris, and you can call me Panos. I'm the Photonic Technology Program Manager in EPIC, and I would love to start with a video for EPIC. Perfect. What a nice video to start with today's online technology meeting. So for the new face in our audience, I would like to say a few things about who we are. We are EPIC. We are the European Photonics Industry Consortium, and we are the world-leading industry association that promotes the sustainable development of organizations working in the field of photonics in Europe. We now count almost 800 members, and we keep growing. The areas that EPIC is active are many and variant, as we also saw in the video at the beginning. We organize technical workshops and roundtables. We serve and sustain a highly valuable network. We help you with market intelligence with the support of Tracy Vanik. We help you raise capital, and we support HR activities as well with the biggest website to find a job in photonics. In this slide here, you can see all the rest of the people behind this great effort of EPIC. Let me now pass at our today's topic, which will be on quantum communication and QKD. The plan of these meetings, as all the online technology meetings of EPIC, is to create new business opportunities, to connect the people and to introduce one to each other. And today we're going to listen what are the existing solutions in the market for quantum key distribution systems and what are the needs for going towards implementing those technologies into our existing networks. I'm sure that we will be able to create important connections and new collaborations. And at this point, I would like to thank our partner for this meeting today, which is the Quantum Business Network, and the sponsors of these meetings. So the sponsor of the meeting today is QuTech, which represents a local ecosystem of companies creating scalable prototypes of quantum Internet and quantum computing. Quandela, that provides and integrates bright and big-tailed single-photon sources into systems to develop a photonic quantum computer. Notably, Quandela will release a 6-qubit photonic quantum computer on the cloud by the end of this year. fibeReality, which is independent consulting and market intelligence company specializing in optical equipment and services in the telecommunication and data communication space. Phix, that offers cost-effective manufacturing service for photonic integrated circuit-based modules in large volumes. Excelitas, that delivers innovative, high-performance solutions to meet the lighting, detection, and optical technology needs of original equipment manufacturers. iXblue, which is also speaker today, is a leading global provider of innovative solutions and services employing quantum technologies for navigation, positioning, and imaging with fiber and fiber components. Modulight, that focuses on designing, developing, and manufacturing laser diodes and laser systems for medical, industrial, security, defense, and display projection markets. And finally, we also have TeraXion, which is a pioneer of fiber Bragg rating technology and narrow linewidth lasers. Based on FBG, the company offers a wide variety of narrow optical filters and chromatic dispersion receptors that help optimize QKD systems. TeraXion has also developed a 1550 nanometer DFB laser with a line width below 20 kilohertz to enable new optical communication and optical sensing applications. And here you can see an overview of all the upcoming technology meetings for the next 4 months. But I would like to draw your attention for today's audience in the following 3 online technology meetings. On CMOS compatible integrated photonics, actually this one is a physical meeting that happens in Leuven at the beginning of September, 7 to 8 to be more specific. We also, I would like also to highlight the fact that we have another online technology meeting coming soon, 24th of October, on satellite quantum communication, and 21st of November on peak testing. And I would like also to highlight for today's audience the Industrial Quantum Photonics Technology Summit that EPIC is organizing this September, 7th to 8th of September, in the University of Glasgow. In this event, we will bring together the European quantum industry ecosystem to commercialize upcoming products from the current R&D initiatives. We will discuss the second quantum revolution, its application and challenges, and what role Europe is going to play in this emerging market. Let's give a look at the supply chain of this meeting. We already have for this a lot of people register. Big companies, big names will be there. Please do not forget to register and come and meet us in person. And now I would like to share with you our new promo video for this event.
Quantum is one of the decade's most disruptive technologies that is changing the world as we know it. Quantum applications allow us to process information more efficiently, measure nature more accurately, and connect to the world more securely. EPIC supports quantum technologies, and the next Industrial Quantum Photonics Technology Summit will gather experts and leaders from industrial companies to discuss the second quantum revolution, its applications and challenges. And we couldn't have a better host than the University of Glasgow, not only for its magnificent buildings and notable alumni like Adam Smith, James Watt and David Livingstone, but because its Centre for Quantum Technology aims to be a world leader in the field. During this EPIC meeting, we will discuss the 4 primary application areas in which a paradigm shift is expected. Quantum communication is advancing quickly, with industrial applications being visible today. We'll discover the trends of these quantum communication applications and what's still required to deploy them in our telecommunication networks. Quantum computers are now a reality, and the photonic qubit is one of the most promising for upscaled quantum processors. Connecting with industry to accelerate quantum computing solutions is essential. Quantum sensing is leading the way toward the highly accurate measurement of physical parameters. Advances in this area have applications across the board, from healthcare to navigation to archaeology and everything in between. And in quantum imaging, we are developing multidimensional cameras operating across a range of wavelengths, timescales, and length scales, creating a new industrial landscape for imaging systems and their applications in healthcare, transportation, space, defense and security, and the environment. Internationally renowned experts and the companies that are now setting trends will join us for this EPIC Industrial Quantum Photonics Technology Summit. Let's meet at the University of Glasgow and together dive deep into the fantastic world of the second quantum revolution.
Perfect, that was really nice. So everybody, we're waiting for you to register for the Quantum Summit in September. We're looking towards meeting you in person. So now back to our today's meeting. If any of you would like to get introduced to any of the other participants of the meeting, they can always contact me afterwards in my mail, panagiotis.vergyris @epic-asoc.com, or to my colleague Antonio Castello. You can also see his email here, with whom I'm co-moderating this event today. Of course, everybody in the room is encouraged to actively participate in the meeting and ask all the technology-related questions that you have. You can, of course, put it in the chat and we'll bring it in the room to share with all the participants. And before I continue, I would like to remind you that those meetings are recorded and live streamed on YouTube. And I would like to pass the floor to my colleague Antonio Castello. Antonio, can you please let us know what is going to happen today?
Yeah, sure. Thank you, Panos. It's a pleasure to be here, and good afternoon, everybody. As you can see today here, we have an impressive chain that shows the interest of the quantum communication and quantum technologies, not only in our members, but also in all over the world. The supply chain is really full of interesting companies, from end users that we cover most of the markets, from telecom to space and defense, cybersecurity, also the semiconductor manufacturing equipment and 5G communication. Of course, we have photonic integrated circuits and modules companies, also equipment manufacturers and components, from lasers to optics, fiber optics, of course, different quantum computing solutions, optical design as well, optical network, market intelligence and consultancy. Is very important that those companies are interested in quantum technologies and support all the people working on that. And I also would like to highlight the big big interest of a lot of R&D centers that show what's the tendency nowadays. You can see an impressive amount of universities and research centers over Europe that are working, or at least they are thinking in quantum technologies for their future research. So, well, welcome everybody. And Panos, what's next? What's the schedule for today? Who is the first speaker?
Thank you, Antonio. Thank you. Really impressive supply chain. It's true. So now back to our meeting and our setup today. Today we're gonna listen Antonio Manzalini, the senior project manager at Telecom Italia, and we will continue with Gert Grammel, networking with network strategy at Juniper Networks. We are happy also to have Maxim Kuschnerov, director of the Optical and Quantum Communication Laboratory in Huawei. We have Kevin Fussell, the CEO of Quantum Optics Jena, Baptiste Gouraud, research engineer at iXblue Photonics, and we also have Vanessa Diaz, which is a business development director at Lux Quandela. Here I would like to stop sharing my screen, and before we continue with the presentation of the speakers, I would like first to thank once more Johannes Vers from QBN for helping me building this meeting today. And Johannes, you would like to say a few words about you and what you're doing?
Yeah, thank you very much, Panos. I think you and also the video also mentioned the huge impact quantum technologies can have and will have in the economy and also in a societal way. Yeah, I want to mention that during my time in the photonics cluster, in the cluster management of a photonics cluster, Epic and Carlos were an inspiration and role model for me in terms of cluster development. And as Epic represents the most quantum technology suppliers, I'm more than happy to collaborate now and stimulate and assist cooperation in our members of our members together. So let me share my screen for a quick overview of QBN. So here we go. Yeah, so my name is Johannes Verst. I'm quantum physicist, CEO of QBN, and a co-founder of the Black Quant Fund. QBN is the global business network that promotes networking, business creation, and the development of organizations working in the field of quantum technologies and its value chains. We bring together people from industry, science, politics to build a strong quantum industry in Europe. And this is we, so the most important key players ranging from large companies, SMEs, and startups to RTOs, universities, ministries, public bodies, and investors from all across the world. And yeah, together we are working to build a strong quantum industry. All these companies and organizations are working in different disciplines of quantum technologies. For instance, quantum computing, hardware and software, quantum communication and cryptography, quantum sensing, imaging, metrology, the enabling technologies like photonics, and all the application areas. And yeah, to provide our members with growth acceleration and to build a strong quantum industry, QBN's activities and services cover 5 pillars in total. First, the platform. So QBN provide a platform, especially our working groups on the different disciplines mentioned before, to provide and promote business collaborations, knowledge exchange in a trust-based environment. We support technology and business acceleration, including technology transfer, innovation support, entrepreneurial mentoring, startup support, for example, with fast access to private and public funding. We provide marketing support to gain visibility of quantum in general and our members, of course. We support lobbying to build a sustainable structure or sustainable structures for our members and the whole community. And finally, we do a little bit of consulting, for example, developing roadmaps together with enabling technology companies, or we develop business use cases for industry end users, for example, for quantum computing. And yeah, if you want to stay up to date, follow us on LinkedIn and Twitter to receive the latest news in quantum, jobs, events, funding calls, and so on. And if you want to learn more, please contact me on LinkedIn. And now I'm looking very much forward to today's presentation, especially the news from Kevin from Quantum Optics Jena. And with this, back to you, Panos.
Thanks a lot, Johannes. Thank you. Then you can stop sharing your screen. And thanks again for helping with this event. And now I would like to ask also Natalie Debaz to let people know what PhotoHub is doing, what's our activities, and who can profit from PhotoHub. Natalie, if you can share your screen.
Okay, good afternoon. Thank you for your introduction. So are you maybe a company who would like to explore and make advantages of the photonics technology, but you don't have the expert in-house or the technology? Or are you a company that would like to receive support from top experts and top technology, maybe in building your prototype or for upscaling? Or are you looking for hands-on training in photonics? Or are you looking for support in finding investment support? There is one address, photonhub.eu. It's a European project that acts as a one-stop shop for photonics innovation. And especially for the people that are attending here, the webinar, we can offer free assessment by top experts. So please go to our website, photonhub.eu, register, and please mention also in your description the EPIC webinar. And then we will get in touch with you and connect you with one of our best experts. Thank you.
Thanks a lot, Natalie. Thanks a lot. So be aware, everybody, about PhotoHub and just spread the news about it. And again, thanks a lot, Johannes. Thanks a lot, Natalie. I would like now to pass to our meeting and ask our first speaker to share his screen, which is Antonio Manzalini from Telecom Italia. Antonio? Perfect. The floor is yours. I assume you're muted?
Oh, yes, thank you. Thank you very much.
Perfect.
Can you hear me now? Yes?
Crystal clear.
Yeah, thank you very much. So first of all, I wish saying that it's an honor and a pleasure for me being here today and making this presentation. So thank you very much. So good afternoon to you all. My name is Antonio Manzalini. I am from team Telecom Italia, where I'm working for the innovation department. My brief talk will be on technologies and application on this so-called second quantum revolution, specifically what we are doing in team currently. Well, I'm talking about second quantum revolution because, you know, a first quantum revolution already happened some decades ago because, you know, the basic principle of quantum mechanics are at the basis, you know, of microelectronics, chipset developments. So you may think about the impact of the first quantum revolution. So today, when talking about the second quantum revolution, we see a growing interest. We see a growing interest worldwide, a growing interest with a number of indicators and evidences, which we are putting on which we are putting attention. For example, there are several experiments and field trials worldwide and the industrial level, not only in labs, not only in research and academia center, but also in field trials, in network operators and service providers are deeply engaged. There are a number of private and public investment you see in this slide on the right hand side. At the bottom, some figures about investments worldwide, really impressive. Looking at the number of patents, well, that's another indicator, interesting indicator. The number of patents is growing exponentially, mainly on quantum security, but also in quantum computing. And then what about the startups? Really increasing number of startups and acquisition. And then also importantly, there are efforts in standardization bodies. The importance of the work done in standardization body for an industry like a network operator. So we are putting particular attention to that as well. What are the main application areas? Well, you know, there are four main application areas One area is about quantum communication, so the idea of using the quantum effects, the no-cloning theorem, and in the future maybe the entanglement for transmitting digital data in a quantum secure way. Our attention is currently focused on quantum key distribution, obviously, which is the technology which has higher technology readiness level in the area of the technologies of the second quantum revolution. But we are paying attention also to the long-term evolution towards the quantum internet. Should the entanglement be mature in the next 5-10 years. Another area is quantum computation, where the superposition effect is being used to develop a new kind of quantum computers to speed up the data processing. And this is extremely interesting when you have to solve very complex problems. Optimization problems. Then quantum simulation, quantum sensing, and metrology. Clearly, the different application areas may have different impacts in terms of timing, and you see in the right-hand side of this chart a tentative roadmap of these technologies. What we're doing in team basically is summarized in this chart. The team group through Telsi, which is a company of the group, acquired a stake of shares in Quantum Telecommunication Italy, which is a spin-off of CNR in Italy. So we are pursuing theoretical and experimental activities together with Telsi, company of the group, and QTI, this startup of which we have acquired a stake. Experimental activities on quantum key distribution, basically exploring application scenario and exploitation of services. We are having collaboration with universities in Europe and in Italy, above all on quantum security and computing. We participate in the European projects, European project of the quantum flagship, but also we are participating in the initiative of the Euro QCI, the Euro Quantum Communication Infrastructure. I've already mentioned the importance for us of being present and contributing to the standardization activities. And then we are also producing as activities in the innovation department, trend reports, technical communications from the Telecom Italia group on quantum. And we have set up together with some university and institution in Italy, as well Quantum Academy, which is really, we believe, important, also the education, the formation of the personnel and also of the people which are in the Italian ecosystem. This is just an example of a project funded by the European Commission in which we are participating. Is QSafe. It's one of the two projects. The other one is Octavo, which have been approved by European Commission in the context of the EuroQCI initiative. The objective of this project, I'm answering you just as an example. What we are doing is to define the functional system architecture of this quantum shield across Europe based on quantum key distribution, the implementation roadmap, including the costs, the timeline, and the focus is basically in this project on quantum key distribution for optics in optical networks. Consider that the European Commission has the objective to run a demo of the EuroQCI by 2024 and aiming at initial operation services by 2027. So, from these figures, you are realizing even more how the market is becoming very, very mature, and the technology readiness level of QKD is really very high. The project to consider also the integration, obviously, of land network QKD with space QKD and also with post-quantum cryptography, and it keeps an eye also to the evolution towards the quantum internet, maybe in the long term, 2030 plus. This slide is an example of our participation in sensation body. You know, it's important for an operator to follow, to contribute to the sensation body of these technologies, because before the exploitation of any technology, the pieces of equipment, the pieces of node should be standardized in their interfaces, in their functional architecture, in order to be ready for being integrated in current network. Not only from a transmission viewpoint, but also from the management and control viewpoint. This is basically a hot issue in all the standardization bodies. I'm listing in this picture in GSMA, in Sensenelec, in ATF, in ETSI, in ATU. Specifically in GSMA, we are having a chairing position. We set up a group on quantum networking and services already in 2019, and we produced in 2021 2 white papers, which are available at the link I reported on this slide. That's all. Thank you very much for your attention.
Thanks a lot, Antonio. Thanks a lot for a really nice presentation. Thanks a lot for being here today and sharing the point of view of Telecom Italia about quantum technologies and quantum applications. I'm sure we're going to listen later on also a lot of our speakers offering solutions on how to implement those new technologies in our nowadays telecom systems. So now it's open for questions. You can ask whatever you want to Antonio, but since we brought the level of discussion higher into the way to implement those technologies into our real networks, my question is, do you have a feeling what we actually miss when it comes to photonics in order to have a fully employable quantum key distribution system for the telecom network of nowadays?
Yes, thank you. Thank you very much for the question. Yes, sure. As I mentioned previously, it's important that we reach standard functional architecture and standard interfaces for the pieces of equipment which will be integrated into the current networks. So for quantum key distribution nodes, it's important that they will be interoperable at the transmission level, obviously at the physical level, with proper parameter at the interfaces. But it's important also that the interoperability will be at the upper layer as well. Upper layer, I don't mean the application layers, I mean the upper layer concerning the operations. So it's important that we have standard interfaces for the management and control and the orchestration of these pieces of equipment as well. This means that we need to define the proper abstractions, and that's actually what we are doing in GSMA, for example, and that's what they are starting doing also in ETSI, the abstraction of the internet hardware of these nodes and the proper interfaces API. Thank you.
Okay, thanks a lot, Antonio. Thank you. Do you have any other question for Antonio? These are your chance. Yes, we have one from Mark Wilkowitz from fibeReality. Hello, Mark.
Hey, how's it going? Antonio, given that you have a good overview of what's going on with quantum, I was just wondering if you thought that in what was the subject I wanted to get into here? Sensing, sorry, in the sensing realm. It seems to me that the sensing realm is quite mature, and I'm just wondering, again, given that you have an overview of what's going on and maybe don't have any particular bias, whether you think that has the least risk for European companies in moving forward, given that there's been so much work done in quantum sensing.
Well, quantum sensing is, if I understand correctly, the question is an extremely important area of application, obviously, as well, for a number of reasons. The potential industrial impact is extremely important. Well, clearly, the question is, you're asking about the potential risk, right? Risk and opportunities right? The question is understanding the sustainability of the market. First of all, it's important to understand what are the potential customers, what are the potential use cases and applications, what are the expectations of the markets, in order to provide a timely and with the proper technologies and the right technology readiness level, the solution. So it's a matter of finding also the right balance in the sustainability of the market. Thank you.
Thanks a lot, Mark, for the questions. Thanks a lot, Antonio, for answering. You have another question? If not, I would like to call the next speaker, who might also give us some solutions regarding what we're discussing now, which is from Gert Grammel from Juniper Networks. Gert, would you like to share your screen? Hello.
Yeah. Let me share my screen. Give me a second. Oops. No.
Perfect. The floor is yours.
Okay, thanks for the invitation. Thank you for EPIC. That is really a great opportunity to speak to the community. So my name is Gert and I'm with Juniper Networks. So what is Juniper Networks? We're basically a networking company. So think of it as a kind of a little brother of Cisco. And we are in the business of networking routers and switches and also in the cloud. In Juniper, we currently have what we call a Pathfinder mission, where we explore new technology and develop also solutions. And we currently looking into the quantum key distribution and quantum random number generation as the two potential, let's say, leading ideas on quantum technology that could influence the networking area. I'm not saying this is the only one. We would be ready to look at everything that is quantum related, but those are currently front runners, and we're looking into those technologies. Also, what we don't do, we are not investing into quantum computers, QKD or QRNG. So the idea here is really to create a kind of a partnership with companies that do those kind of things and come up with joint solutions by leveraging what Juniper can bring to the table, namely networking and networking solutions, and combining them intelligently with the quantum technology. I mean, the classical thing obviously is QKD. So our experience with working with some of our partners so far were, okay, they kind of have a QKD and they kind of consider their job done when a key is distributed. But that doesn't help a lot of in the industry because the key needs to be consumed. And it's the consumption part that is not very well defined, unfortunately. And also standards often do not help us in that. So there's certainly something to investigate and develop there. Also, in terms of QRNG, so quantum random number generators, these are better random number generators than what we have so far, which are not quantum. But the big question is, how much better are they really? And how can we exploit that kind of betterness of the random number generation for really well applications? Now, what do we want? Essentially, we want to new ideas to putting into practice. So we work with technology partners on innovative use cases and develop concepts in leveraging quantum technology and networking. So that's our current focus. And we are pretty open when it comes to working with partners. So there are a lot of, let's say, startups, small companies. So absolutely, if there are some unique ideas that they bring to the table, we would be more than happy to engage with them. And we're also obviously engaging with network operators to jointly evaluate the value of quantum technology. So this is not only a kind of a, let's say, Juniper evaluation back in the lab. The idea here really is a kind of a three-way collaboration with operators, system or networking companies, and startups to come up with unique proposal for solutions. And that's the end of my talk, and I'm happy to take any question.
Thank you very much, Gert. Nice presentation. As you are, let's say, offering the possibility of sharing ideas to work with you, which are the challenges you face up to now when talking with companies working in quantum to be participate in one of your projects? I guess that the communication sometimes or the language can be different. So which challenges did you face up to now?
I think one of the biggest funny things actually is the definition of upper and lower. Because let's say in our visualization, the quantum key distribution would be above the networking, while if you go into QKD, the networking is above QKD in all the slides. So that creates a lot of confusion if you talk about upper layer, what exactly is meant by that. There are other funny things more about key exchange. So obviously everything, let's say there's the idea in the network that you take an ETSI QKD 14 interface and everything's done. Unfortunately, I have to tell you, no, it's not. There's there are a lot of things that need to be done in order to really make it work in a real networking environment. So that is, I would think, currently underappreciated, both on carrier side and also on vendor side on QKD. And then obviously, it depends really on your partners, on their professionality. What you can really do with them. We appreciate partners that are flexible and you can work with them openly. But obviously sometimes there are company politics thinking, hey, there's something we need to hide from one or the other. That makes things a little bit difficult. But at least on our end, we are open. We are happy to work with everybody who can bring something on the table. And in the end, it's about bringing innovative solutions to the world. It's really not about quantum key distribution or QKD. It needs to be put into a solution, and that's the key.
Very good. Very good. Thank you for your answers. So we have here a lot of providers and manufacturers of quantum solutions. So I hope they can find something interesting to share with you and find a new project. I don't know if you have any other question. Sorry. Panos. Yes, please.
Yes, I would like to have another question. I mean, now the rest of the speaker will be more on the technology and they have to offer to big networkers and telecom providers. My question is once more, I mean, you have this slide speaking about solutions. Can you please give us some more hints when it comes to technology, really into technology, what you're missing for going to a broad implementation of the QKD systems?
Well, let's say one of the difficult things, basically, of any kind of new technology, although everybody says it's revolutionary, it's often just a kind of incremental improvement over what you currently have. So let's take the example of quantum random number generators. So, I mean, okay, you have a better randomness or better entropy by doing so, but is the entropy that you're using today is so much worse than that you really need to get rid of them? So those are the questions. It's really about the differentiation. How do you make the business case or the use case really catchy? And the other one, and that hits more the QKD side of things, is about qualification and product testing. So if you really want to deploy let's say a QKD-based security solution, somebody needs to certify that your QKD system is really safe, right? I mean, you could theoretically, put a system into place that does everything else except quantum exchange. But somebody needs to qualify, say, yes, it is what it does, and it's really a QKD system, and you cannot break it. And that kind of infrastructure is not there yet. So from let's say business perspective, I think that is kind of slowing down things a little bit. We do not see that there are, let's say, a lot of even standards. So standards are working on it, but Even if you have a standard, you need to test the standard to make sure that your equipment is according to the standard. And those tests reports or test specifications need to be built as well. And that's really a challenge today. So I would really encourage everybody who works, in particular on the security side, to think about how do you want to qualify your equipment or your, let's say your chip or whatever is the building block you're coming up with. How can you qualify that this chip or this solution is doing what it is supposed to do?
So yeah, thank you, Gert, to give us several tips to think about, so all the participants can think in their solutions and how can they be implemented. So please, Mark, another question from your side. So
yes, thank you so much. I found the Juniper, the gentleman from Juniper's presentation to be very refreshing. I think he's asking a lot of questions about quantum that other people are asking as well. And I just wonder if he has just a personal opinion that, especially for European suppliers who, I mean, I think we all want to have European vendors get back to the status of the past where they had a leadership position at times, in optical. They were amongst the leaders. And I'm just wondering if too much time, and this may be blasphemy in a forum like this, but is there too much emphasis being made on quantum given some of the responses you made? Or are you somewhat bullish about QKD and the random numbers and all this other stuff happening?
That's a very good question. Thank you for that. Let me briefly think about how to answer it. I think one of my personal observations is that the whole industry in quantum is pretty fragmented. And that makes things really difficult. In particular, if you really work in a security environment, you need to have standards. If somebody comes to you and say, hey, I have a new proprietary mechanism that I'm not going to disclose, that is better than what have you in terms of cryptography. If you have a serious company, the short answer is no. Go home and do your homework. It really needs to be an algorithm that is open, that everybody can look at, that can scrutinize. It's kind of a little bit of the open source kind of thing. And I personally believe that we need something like that for QKD as well, if we want to be successful. Because in the end, it's really such security relevant that 1,000 eyes need to look at it and try to break it, and we need to improve. So in order to really make it happen, we need something like that. We really need not only a test specification and say this is the way I'm qualifying the QKD system. We also need a way really to say, okay, how do we improve it? So somebody comes up with an idea on how to attack a QKD device, right? Okay, what do you do then? So you know it, you put it out in the press, and now what? So there need to be some infrastructure that helps users of those devices to do the next thing.
Thank you, Gert. We have another question from ID Quantic. Thomas Lager, please.
Hello, this is Thomas Langer, ID Quantic Europe, Vienna. I just wanted to note about security certification of QKD equipment, that the ETSI QKD is working on it, and also the ISO SC27 Working Group 3 is working on security catalogs of security functional requirements for the common criteria security specification of QKD equipment. And so I found it particularly very interesting how you mentioned that it's very necessary to qualify the equipment, to test the equipment, to develop the methodologies and all this background documentation. And there is a lot of activity going on, so people are aware of this, and it's especially the ETSI ISG QKD where people are active in this domain.
Yeah, thank you for mentioning this, because in the end, I think this kind of shows a bit of a leadership position of Europe in that space. because we are taking these practical problems. So in terms of ETSI standardization. So from that perspective, I really love that it's taken on, and obviously we are following it and we are aware of it. There's one little thing about standards or standardization, which is valid for ETSI, and here I also would like to acknowledge my earlier speaker, Antonio Manzalini, who was working in ITU. So if you think about optical networks, at least in the past 20 years, they were back-to-back systems. So basically, you didn't qualify transmitters and a receiver; you qualified a link, which is how ETSI also does its job. But the thing is, the link becomes a black box, but that is exactly where you do the attack. I have to say that, again, from a security perspective, that is not how it should be tackled. But standards do what they want to do. But my personal take is there needs to be a follow-up.
Yeah, this is absolutely my opinion also. Yeah, the link has to be included. This is very much my opinion, and so we are working on it really in this direction. Yeah. And
yeah, welcome. Okay, we're doing it step by step, right?
Yeah,
so
right.
It's not a
right.
criticism.
Right.
No.
So actually, the German BSI is involved in this evaluation stuff. So we have really also the expertise in the background, and probably also we'll focus more on the telecom view of the QKD link. And so I know very well how it is this discrepancy. They are going now for the security specification of the boxes, of the end boxes, and somehow omitting the link. But it's very clear to me that you should go for security certification of the use case, so to say, for the link on the link level. Thank you.
Thank you, Thomas. Well, we will have also time after the presentations for a longer discussion, so keep your questions in mind. But I would like to pass to the next speaker. We have Maxim Kuschnerov, Director of Optical and Quantum Communications Laboratory at Huawei. So Maxim, whenever you're ready.
Yes, thanks.
Perfect.
You can see my screen? Okay.
Yeah, we see your screen, so thank you.
So thanks for the invitation. Today I wanted to talk about one particular way of implementing QKD using continuous variables and demonstrate which type of performance one can expect these days from this technology, what we have, let's say, developed here in our research department in Germany. So if we look at the basic, school of thoughts for quantum key distribution, of course, we have the discrete variable, counting photons, and the continuous wave, the one that I'm here to talk about. For the continuous wave, simply speaking, we transmit a very low power signal, say a QPSK signal, which we consider as QPSK. Of course, most of the what we detect at the receiver is noise, and we are limited by short noise at the receiver, and this short noise is our quantum random generator, which helps us to generate a random key. And the analysis of this received QPSK signal gives us the ability to generate a key. And the beauty about this system is, if I look at the block diagram, and I hope I don't lose any of you here, the building blocks of the CQKD system are quite straightforward. So it's nothing which one cannot buy today, or nothing which would be too hard to integrate, to be smaller and cheaper and go for larger volume. So all of these components, whether it's the lasers, the modulators, the attenuators, or balanced detectors, are can be off the shelf if we talk about a already functional pre-development prototype. And also they can be very easily shrunk down to very integrated small circuit. And most of the complexity of the system is actually in the protocol and software layer. For example, to one hand, to calibrate the short noise of the balance detector, because this short noise decides about the calibration of the short noise, helps us to identify if there is an eavesdropper in the link, because any kind of interception that you would can expect from an all-powerful eavesdropper would leave a trace on the short noise level. And also we measure, calibrate short noise and the span loss independently. And on the other hand, of course, there's a protocol to distill a key from the detected low power signal. So even if the eavesdropper gets 100 times more power than the actual receiver, we're still able to with security to say with certainty that the key is safe according to the protocol and also the laws of physics. So how does such a signal look like if we detect it? Because it's a different level of abstraction. As said before, we look at this as a QPSK modulation. We transmit a QPSK modulation, and what we receive looks like noise, but actually down inside, if we draw the mean of each of these colors, which is a transmitted symbol, we see that the means are slightly separate, although of course in total these clouds largely overlap and lead to a very high error rate, so well above, let's say, 40%. So, and also if you one more indicator of how mathematically low the received power is on average. Of course, most of the signal we receive is noise, but if we compute an average for this continuous variable system, could be like as low as 0.05 photons per received symbol. So in this spectrum, I find it illustrative to actually emphasize that this peak here, what we see here, is not the quantum signal itself, because it cannot be this high. It's the pilots which we send to be able to lock on the actual quantum transmission. So the pilots are a bit higher power. However, the actual quantum signal is several orders of magnitude below the noise level. It's hidden somewhere here, so it's undetectable to the eye, and requires such a pilot to be rightfully tuned. So of course, natural question, given this technology, what can one expect in terms of performance and reach, right? Because in the end, these are the key performance indicators also for operators when discussing QKD systems. On the left side, we see a transmission reach assessment. The x-axis, the reach itself in kilometers. On the y-axis, the key rate. Now, the absolute value of the key rate, doesn't need to be, that high, because the key is not generated, continuously, but maybe for each link, one key every few minutes. So the absolute speed is maybe not of importance, but just the ability to generate a key in certain human intervals. And we see that the distance that we can bridge, a single span transmission using these devices is in the range of 80 to 100 kilometers. I also might add that the protocol assumptions for security proofs that are the basis of these key rates, in this case, are the most strict ones. And where we assume that most of the link is not trusted. For example, if there is an optical multiplexer, which is used to bring the signal on the fiber, the loss of this multiplexer in this case would be not trusted, or the loss of the fiber itself, although this it cannot be physically below a certain level, in this case also would be not trusted. And if one makes certain practical assumptions about the level of trust one has towards the system, the switch can be extended quite significantly. But of course, for the worst case, all-powerful attacker, one needs to have a certain worst case baseline, which is today this curve here. Also, I might add that CDQKD is a bit more tolerant when it comes to neighboring channels, which has two consequences. On one hand, we can put it in a system, say if it's in the metro city network, where you already have classical signals operating in the C-band, and you can also just add the QKD signal in the C-band without gap which is too big, and still be able to have a functioning system. So there's no need to either have a dedicated fiber for quantum key distribution, or to have the a very large spectral gap between the classical channels and the quantum key distribution channel, which of course, let's say if you go towards the O-band, then eventually would lead to much higher loss for the quantum signal. So of course, this tolerance we have here, kind of the distance, maybe we could have a 20 to 30 kilometers co-propagating system is, a bit shorter than what I've shown here, and also the power levels of neighboring channels may not be, the level that we normally have in the classical telco system, but it's an, added capability of the whole design, which could potentially be exploited for benefit at the system level. And what I'm talking here is not just, PowerPoint or kind of, lab work, it's something more sophisticated. And I think this chart, which, although it might be busy, brings the message that I actually want to bring is our systems are part of a multi-vendor, multi-operator field trial, which is currently run in Madrid as part of the Open QKD network. You see here we have several system vendors and also several quantum key distribution providers together with our system, and we have here deployed 10 of our boxes, which in the look and feel and the dimensions and the performance rival the commercial products. So although we do not, in my department, do any actual product development, these pre-development devices are at the level of the competition in terms of reach or form factor, the other key parameters, and they're seamlessly integrated in the OTN systems, right? So they interwork and they pass on keys to OTN layers or to dedicated encryption boxes by, in this case, it was Rodo and Schwarz. So it's a seamless integration. They work in the C-band, and also one nice benefit is a single transmitter box could work, to an optical switch and interface with several different quantum receivers. So there's no need to have dedicated, paired links. One can save in hardware by having a little hub in the middle of the transmitter, and then sending out signals in different directions using an optical switch. So it's potentially a system which could reduce overall system complexity. So to summarize, our solution that we have investigated and brought to a certain level of maturity is proven in the field, real network to be robust and functional. We believe that it's the inherent advantage of this QKD design. It's its path towards a lower cost implementation. I mean, there is no real blocking point. If we analyze the components like just simple modulators and simple detectors, I don't see blocking points of why this couldn't be miniaturized and scaled up to much higher volumes, much lower cost, which we need at some point in the future when demand picks up. So maybe one final thought, we are looking for European partners on QKD. I'm saying partners, not customers. Potentially for companies which are interested in, ODM functionality or distribution, just to get engaged to create a more robust and diverse European ecosystem with QKD. We have an open door. We believe to have a very nice technology to be, which can contribute to the European QKD marketplace. So with this, thanks very much.
Thanks a lot, Maxim. Thanks a lot. That's really nice. It's already triggered a lot of questions to the audience, and I'm not going to lose time. I will go directly to the questions coming from the audience. The first one comes from Chris Maloney from VPI Photonics. Hello, Chris.
Hey, Panos, and thanks, Maxim, for that. I have one question just around adding these QKD systems into existing classical channels. There's so many different types of deployments and technologies out there. Do you find that to be a a large challenge to address, is adding these QKD systems to, you know, networks that are already out there?
I mean, if you know, to talk about to add these very low power signals to you know, the same fiber, just general Raman scattering, you know, is some mechanism which prevents, let's say, too much flexibility. So our system is more tolerant, but also it's also not all powerful. I mean, you've seen the limitations. In order to have a certain co-propagation, either the reach or the power levels of the classical channels would need to be adjusted. So it's nothing which works, you know, totally seamlessly. So there's still things which need to be done to, you know, make it all kind of, you know, all capable. But today, it's I just don't see that happening yet.
Okay, thank you. But Chris, really nice question. You have something to show us regarding that and solution?
Yeah, I have one slide here I can show quickly. Yeah, at VPI Photonics, we do have a simulation tool for QKD applications. It's an add-on to our existing tool, VPI Transmission Maker Optical Systems, which is typically used for classical systems. And so this toolkit is for system level CV and DV QKD. And so I brought up that one question about these coexistence scenarios. I'm finding, you know, in my discussions with those who are developing these types of systems, that the coexistence scenario is a interesting use case because there's so many different types of deployments. So you can see in this image here, there's an example of a 16 QAM channel that we've added a CV QKD system to. And so both signals are passing through the same fiber, and you can see how we can, you know, analyze the Raman noise floor and how does the quantum channel, how is it impacted by the existing classical channel. So in our software, we can do some system design, explore these different types of scenarios, and account for component imperfections. So I know we have a single photon counting module that can, you know, account for dark count rates after counting and such. So I think this could be an interesting solution to help you know, progress towards implementation in the real world. So thanks, Panos.
Thanks, but that's a really nice solution, Chris. It's a really nice tool, actually. I suppose that not only the people that they are bringing here continuous variable systems, but also the ones that brings discrete variable system will be highly interesting to have it. Thanks a lot.
Yeah, thanks.
Yeah. Thank you, Chris. And I would like to go now to the next question. The next question comes from Tracy Vanik. Tracy?
There, I think I'm unmuted now. Oh, wonderful. Thank you so much, Panos. You caught me a little bit by surprise. So, Maxim, I really liked your presentation. It was very interesting. And but I have a question. How do you detect the eavesdropper on the fiber? From what I could tell, it looked like basically measuring the signal to noise floor and looking for variations. But is that correct, first of all? And then second of all, is there any variation with vendors that you would see that could impact that? So please, if you could help clarify this for me, I'd be most appreciative.
Sure. So what we do is we do not measure the signal to noise ratio, but actually, you know, the signal and the noise separately. So the link loss and the noise in the system, which is mostly shot noise, and the receiver are characterized and calibrated constantly. So any attack which, you know, is applicable according to the laws of physics would leave a trace on the short noise level. So our main task in building these systems and prototypes is to be able to stabilize and characterize to the highest precision the level to which we can measure short noise in our receiver. And the more accurately we can do it, the more better we can track it, the more smaller the text or the larger the text can be, which we can identify in the system itself. So it's kind of separate detection of the link loss and the noise, so where an attack would lead a trace on the noise level would always kind of enhance the noise level that we measure. And I think the second question was whether this changes over time, right? Did I catch it correctly?
So part of it was, does it change over time, and does it change with different vendors? And I saw that there was a quantum channel. So is the quantum channel always the same with all vendors? Does does the detection of an eavesdropper change in the way that you would approach this with different vendors? Would you expect to see a different signaling, a different signal with different vendors?
I mean, I think the optical schema we use is, peculiar to what we do. So our system doesn't interoperate with any other system, especially if it's a DV system. And also vendors using QKD might just design their own line signaling for their purposes in different frequencies. So in the end, it's a closed system. So Huawei, our box only works with our box. And yes, I mean, it requires constant. So we need to constantly monitor the level of shot noise, which I mentioned in the link loss, because they change over time with temperature and also any possible attack. So it's a constant calibration which happens in our system to track any changes.
Okay, wonderful. Thank you so much.
Thanks.
Thank you. Thanks, Maxim. Thanks, Tracy. And there is one more question that comes from Tom Grabry. I know that Grab3, I'm sorry, I know that yours has something to show us. So, Tom.
Thank you, Panos. Yeah, Maxim, no, that's a really interesting presentation. Thank you. I'm the Senior Business Development Manager from QETS, Quantum Security in the UK. And my question to you is sort of more around the scalability side of things. And I think you said at the end there, you're looking for European partners, but not necessarily on a commercial level. Is that right? So you sort of, as Huawei, are you looking to sort of develop the QKD for more in-house purposes and build them onto things rather than sell them separately as such?
Well, this is a very good question, which we can also discuss deeper offline. But I think what I can leave you with is that I think we are open to exploring opportunities where we can also, I don't know, there's many opportunities like a licensing model. We can just license our technology, which is developed here in Europe, without any, fully locally, but maybe to a European partner. Because in the end, I think the European QKD system, could use more native players who also own, a certain level of technology and manufacturing chain, distribution chain. So we are willing to engage in a constructive way to potentially enable such a new or existing player in the field.
That's interesting. Thank you.
Thank you, Maxim. And Tom, could you also show us what you have there in QETS, what you're doing at the moment?
Certainly can. A very, very brief slide or two. Can you see my screen there?
Crystal clear.
Round. So to say, I'm part of QETS Quantum Security. So we're UK-based, a startup, and we're developing QKD and QRNG as well. And it's a very rough and ready slide, so apologies for the slightly bitter part. But effectively, I'm here to sort of talk about two quick things. We are a relatively small team. There's a picture last year of us by Clifton Suspension Bridge in Bristol. We're about 25 people now, so we've grown quite considerably over the last 12 months or so, and we're looking to grow more, which is sort of my question around scalability. And we're at that point where we have prototype QKD and QRNG, and we are pushing them out to various projects. We're in a really exciting project in Paris, which is one of the early EuroQCI projects. And to that end, I'm here for an ask, really. We're looking for partners in all shapes and forms. We have chip-based QKD, QRNG, and we're looking for people to sort of extend and enhance our supply chain across the UK and Europe. We're looking to partner with people definitely on a commercial level in projects and proof of concepts and obviously sales. But also one of the key things is sort of the end user and the insights that they can provide, all the feedback loops and any partners that we can work with. That I've spoken to a few people who are on this meeting already, to be fair. So quite a few of you probably know QETS and myself. We're looking to step forwards, and certainly in the UK and Europe initially, we've got some really good relationships. But I think EPIC and this forum can really enhance that. We've got some real expertise in the team already, down in the bottom right there. And let's say we've grown that further, and we can provide vast amounts of expert advice and consultancy support, as well as the actual hardware, and working with other companies and organizations. We've talked a lot about standards already, and ETSI and the BSI and things like that. So we're heavily involved in those conversations as well to try and push those forwards as much as possible, because we understand that is a hindrance at the moment. But the more relationships we can build, the more work we can do to understand each other's products and the interoperability potential, and how we can work together, the quicker we can push the quantum agenda forwards, and make it a lot easier for almost everyone here, I think. That's me in a nutshell, Panos. Thank you.
Thanks a lot, Tom. Thank you. So if anybody has any other question for, not only for Maxim, but also for Tom or for Quiz, that they present their own solutions into the field, just feel free to ask it. And now, Maxim, we have more questions coming. One comes from Noik. Yikan, you would like to ask a question yourself?
Okay.
Perfect.
Yes, I'm alive. Hi, Maxim.
Hello. Hi.
It's Alex. Good to see you, my old friend. So, just to leave my question. So, have you evaluated cost from the photonic part and electronics part of your CVQKD? Because you have very complex post-processing to develop.
Yes, I mean, our system currently looks like this, that we process the protocol in a server. So, so the cost of the server is what it takes to run the whole backend of processing for a, say, small scale volume, in software. If, of course, you then progress towards, potentially very high volumes, in the far future, one can, of course, also, integrate or implement this kind of processing on FPGAs or ASICs. But today it's a server. So, the overhead is always you need to pay for a server which runs the protocol.
Mm-hmm. So currently our team have developed all the photonic solutions for both DVQKD and CVQKD. So which is based on silicon photonics and 3.5 photonics. So we made a fair comparison in the photonic level. So you are right, because in the photonic level, so if we use 3.5 and silicon, CVQKD has a lower cost, but you need to consider the electronics part to all together. That's my point of view. So it is possible DV1 might be cheaper in the future. So that's my think. Thank you.
Thanks for the comment.
Thanks a lot. Thanks a lot for the comment. I would like to go to the next question, Maxim. We'll have quite a few questions for you. So this one comes from Alina Iriscu. Alina, you can ask a question for yourself, if possible, so you can present also yourself.
Hello, good afternoon. My name is Alina Hriscu. I am working for EUSPA. I was curious about the solution you presented, Maxim, in terms of continuous variable QKD and its potential compatibility with quantum repeaters, which is still a research field, but we know that Toshiba claims some quantum repeaters having already been operational.
I mean, from my understanding, we don't have access yet to something which we could call a quantum repeater. So I can't really comment on the level of what Toshiba is doing. Of course, this would be the let's say the long-term evolution of this topic, because as you certainly know, the main limitation of today's solutions is a single-span transmission. At some point, you need to go electrical again to have a trusted repeater. Which may limit the appeal of such systems, because as an operator, may be fine because an operator trusts its own equipment, but as the customer of an operator, you may not have full trust into a network where there is electrical conversion in a quantum channel. So I think where we are today is a first step of many to take, and the future certainly will have to lead us to something like a potential quantum repeater. But again, I can't comment that much on Toshiba's technology in that respect.
Okay, thank you. And for the just another quick question now that I got the floor. Regarding to the parallel multi-coexistent channels in your fiber optic, you have the 3 in your graph, that's correct, that were reaching you up to like 50 kilometers?
Yes, so what I had was like reach up to 50 kilometers, but again, also this depends on yes, so a few channels at 50 kilometers, right? Like yeah, like up to 8, 10. Yeah, like below 10 channels at 50 kilometers was what I showed in that slide. Yeah. And again, the number of channels scales, decreases with distance.
Understood, and that stands true for other type of channels passing through your fiber optics. It don't need to be only quantum channels dedicated to QKD. They can be different transmission.
No, I mean, yeah, what I was referring to having classical channels is neighbor channel to a single QKD channel. So we could, of course, there's one quantum channel on the link, and potentially 10, 20, 30, 40 classical channels. That was the point of that figure, to show how far we can get, how many channels of classical nature next to a single quantum channel.
Understood. Thank you.
Thanks.
Thank you, Alina. Thanks, Maxim. Maxim, I'm sorry, we have 2 more questions. One comes from YouTube. I will go directly for a quick answer, if it's possible, for the one for YouTube, which is very interesting. The question is, what is currently the largest technical challenge to miniaturize the CVQKD system into something like an SFP module, and if that's possible also?
I don't think it's a technical challenge. It's more of a market business challenge. There's, in my opinion, not enough pull from the market for QKD in general, right? And if there's like not enough market pull, there would be not enough invest on the supplier side to miniaturize such equipment further, right? So if, so I think it's mostly a business question, not so much a technical limitation.
Perfect. Really promising answer. So let's go. We have 2 more questions. I would like to keep it quick. Only I'm asking this one as a favor. So the first question comes from Tracy Varnick, our favorite Tracy Varnick from Epic. Tracy.
Thank you so much, Panos. So Maxim, sorry, another question based upon one of your answers to a question from one of the members. So you talked about securing the fiber, and how do you know if someone has eavesdrop processing being done on the server? First of all, are the servers distributed? And second of all, security is only as good as all of the equipment. How do you secure the servers?
Well, if you're in the field of QKD, right, what you can guarantee for is what's happening in the optical domain, right? So on the fiber. Once you go into the actual hut, right, you can't guarantee for anything. Someone just can come in, break up the door, and take the server with you. So this is something which is in the hand of the actual, the hand of the operator to make sure that there's a limited access to those devices. There's nothing which we can provide as part of our optical solution. We can just speak for what happens on the fiber. Everything outside of the fiber is something which needs additional security.
Yes, my concern is that if the server is doing some of the actual calculation based upon the signals that were received on the fiber, if those calculations that would detect an eavesdropper, if the server could be compromised, so that the server could report that there was no eavesdropping when in fact there was. So you may have measured it on your system, but will how secure is that server going to be so that it cannot be hacked?
Well, these kind of software problems, which you all have, and every computer, every phone is not part of our domain, right? Of course, we need to have a certain assumption that there would be, I don't know, a certain firewall, certain protection on the server side, but it's not part of our research. And we need to, But you're right. I mean, the link to attack certain systems is never the obvious one. You know, it's always much easier to go to some backdoor, and there needs to be additional level of security around the server aspect or around the processing aspect. It doesn't need to be a server; can be also integrated, chip which is hidden from the world, FPGA. In any case, once you are in the electrical domain, you're attackable. So.
Okay. No, I'm sorry to get you off of your area of focus, but thank you very much for your answer.
No problem. It's a good question.
Thanks a lot, Tracy. Thanks, Maxim. Mark, please.
Very quick
question. Maxim, try to answer quick.
This will be very quick. Maxim, I don't know whether you had a chance to go to the RUB session at OFC on quantum, but somebody brought up an anti-tapping, anti-fiber tapping type of solution. What do you think about something like that?
I was not at the session, so maybe I'll have to get with Anuli offline and to discuss it. I can't comment right now. Sorry.
Sure, we can do that. And we have a question from Vanessa Diaz from Lux Quanta.
Hi, hello. I just wanted to give Maxim a hand as well. We also manufacture in Lux Quanta QKD. So the questions are very, very relevant because making sure that we have a trusted node is actually one of the biggest jobs that we have ahead. It's actually directly linked to certification. So it's already establishing a few mechanisms that are needed to protect all the optoelectronics that live within the box. But there is yet work to be done. Also, part of the certification is just making sure that we collaborate with other, let's say, programs or aspects of the network that ensure that the link is perfectly safe. Of course, we have a portion, like Maxim is saying, so we have a portion that we are responsible for, but we have to work together with the other layers to make sure that nobody gets in. That's it.
Okay.
Thanks, Vanessa.
Thanks, Vanessa. Thanks for your comment. Thanks a lot, Maxim. Thanks a lot for the very nice and interesting, informative presentation. I would like now to go to our next speaker. Our next speaker is Kevin Fussell from Quantum Optics Jena. They also developed some QKD systems. So, Kevin, the floor is yours.
Thanks a lot, Panos. I hope you can hear me and hopefully you can see my screen now.
Yes, we can.
Perfect. Yeah, hello, everybody. Now we're switching to another type of QKD, discrete variable QKD. And we heard a lot now about prepare and measure systems. I like to go to another topic because Quantum Optics Jena, we are a startup from the founder for IOF in Jena, and we focusing on entanglement-based QKD systems. So a good message to Antonio. Entanglement-based QKD is still available or is just available with our technology. So I like to start my slides to give you a short overview how entanglement is created. There are different opportunities to do this, different geometries, Sanger cavity configuration, cross-crystal configurations. They're working quite similar. So the magic comes from a nonlinear crystal interaction with a pump laser. So we know this process since years, continuous parametric down conversion. So we have a pump laser going through a crystal, and there it generates, with the help of energy conversation and momentum conversation, a signal and idle photon. But how do we get entangled photons out of this? So in our geometry, we use, for example, a cross-crystal geometry. And now think about a horizontal polarized light going into the optical setup. It will interact with the first crystal and will generate 2 photons, also horizontal polarized, for example, around 800 nanometers. And then going a step further, going to vertical polarized light, and here comes the cross crystal in place. So there the crystal is rotated by an angle of 90 degrees. And in this case, the second crystal will react with the pump laser and also create a signal and idle photon. So the magic now happens if we create a superposition in terms putting into a half-wave plate into the optical system. In this case, you cannot make sure where actually the photons were created, and you will get at the end some kind of superposition between horizontal and vertical polarized light. So this will look like this in the lab. So you can see in the back the nonlinear crystals in the cross-crystal configuration. And we think this concept is quite interesting because you have some kind of intrinsic trust relation with the parties because you don't need some kind of electronics to generate randomness. You can use this spooky action. I will go on to this later on. And you have, that's mostly interesting in terms of security, passive elements. So think about Occam's razor or the KISS principle with mostly optics. And at the end, you have a source independent QKD scheme because the source itself will not know what it sends because actually it's a superposition and it is not measured at the source. So you can place the source either to Alice or Bob's side, or you can put it in the middle, or you can put it to a satellite if you like. It creates the entangled photons. You send them to Alice and Bob. You measure in the basis HV, VA, and then creating with the quantum protocol, so detecting single photons. You have to have some kind of sifting, error correction, and of course privacy amplification. But for the QKD community, that's nothing new. To create at the end a secret key. So we as Quantum Xena provide the whole scheme from hardware to software. So customized photon sources, starting from 800 nanometer, going up to the telecom bands, quantum state analyzers, and of course, key management systems and software to actually create keys, secret keys, which you can use. We believe what's unique for us, we think we have a quite interesting and fast QKD system. So the next video I'd like to share with you is the starting of our system. And what you don't look too much to the details of the of each diagram. So what happens now is at first you have to synchronize clocks. So you have two clocks away, kilometers away, and you have to measure timestamps at each clock. And for sure, you have to make sure that the clocks are in a way synchronized. And the other way is we're sending photons through optical fiber or through a satellite link, whatever. You will change the polarization. That means if you're starting with a certain polarization, one arm will have some kind of polarization change. And for sure, you have to compensate for this. So you have to find the reverse function of this change and find a way to implement this without measuring something. And this is the second part of the video. So first is synchronization of clocks. The second part is our polarization compensation module. And I just started a video. So at the beginning, we don't have any coincidences, as you can see in the middle of the diagram. Then we're starting the clock synchronization. It will be done via software. It's quite fast, so we need roughly 6 seconds to synchronize our clocks, and then our polarization compensation starts. And you can see in the lower right, since we have a threshold value below 11% in the compensate or in the quantum bit error, then we will do or we'll generate keys. And that's it. So 20 seconds, then the system is ready to go. It will deliver keys, will track everything, what you do to the fiber. You will see it in real time. So to give you some kind of status of our development, so we just integrated our system to Cisco routers. So we are now able to speak if you have some Cisco router at place operating with the operation system, I think 17.3. Then we are also ready to integrate our solution into your network. And I'm quite happy to share with you that we just delivered our QKD system to the first customer. So what you can see in the picture on the right is the whole system with the EPS on the upper level and Alice and Bob modules at the lower level. Unfortunately, we are so fast that the construction guys cannot fabricate the optical or the dark fiber. So we have to put it in one rack, and the next thing will be going to distance. And I'm also happy to announce we are now working on our telecom wavelength system. So this is a live view of the system working in the lab right now. So at this point, with the lowest level laser power we can achieve, with an average key rate of 10K in this case, and as I mentioned, it's a it's a real-time system. So we are here at LS site, at the local site, seeing every measurement and the polarization. This will be Bob's site or the remote site. There we cannot see everything because we only share the basis. But at the end, we are also using this. For example, here you can see the sifted key rate. For sure, we have to detect some errors, have to verify our keys, and lower or compress more data to one key that we have at the end, or can make sure that we have a really unique key. In our case, or in this system, it's also for some development activities. We generate key pools to attach to different sites, where each site can use, or if you want to have a Cisco router or whatever other device, this system will talk to the ETSI 040 standard. But for sure, we are also open to discuss possibilities using other protocols as well. So that's a quick overview about our activities. Happy to ask or to request to your questions. Thanks a lot.
So thank you very much, Kevin. Really, really nice presentation, and nice to see your developments. So to all the audience, raise your hands for your questions to Kevin. I will start with just a curiosity regarding the components you show that you manufacture. Which one do you think is the more critical or tricky to produce, if not all of them?
Yeah, so let's say we focus on a deep value chain from us. So we want to make the critical components will be fabricated in-house. I think especially if you're talking about security, then it's good to have the whole value chain in our building. At the moment, most critical, or let's say what's driving us at the moment is especially the pump laser stability. There we are doing a lot of research with different suppliers, qualifying different pump lasers to have a stable solution. I mean, this has to work 24/7, right? And the other one is qualifying detectors at the end. So we actually looking also to different vendors for single photon detection to make sure that we can offer our customers the best solution.
Okay, so you have requirements for different manufacturers.
Yeah. So it's good if you do the whole process chain from hardware to software. You know exactly what you have to do at each point. Also with electronics, so we know what we need and can then go through suppliers and requests for, let's say, answers.
Yeah, thank you. So one question from my colleague Tracy, please, Tracy.
I'm sorry, another question. But Kevin, this was very interesting, and I wanted to confirm. So you have, so you've done this in the lab, and you're using loops of fiber in order to simulate the distance. But has it actually been deployed yet? It looks like it has.
So the test was on real optical telecom fiber. So we guess it was even maybe more challenging because you have a fiber spool, right? And the fiber spool has a lot of stress. And the fiber spool, so we don't have air conditioning in our lab. So the system runs from 10 degrees to 35 degrees at the moment. And it does it quite well. So the actual implementation of this delivered system will be done, I think, in August. We are also in the preparation of a long distance test with the source you actually have seen, or the system you actually have seen. So this will be done in July. And then we know how where we are. So, but we don't expect too much trouble. Yeah, we have to.
You're moving very fast. This looks very good. So, thank you.
Thanks a lot.
Thank you, Tracy. I saw another question in the chat from Ali from Hoffer, UK. I don't know if you can switch on your mic and make the question directly. If not, I can read the question. He's asking, what's the wavelength of pump you are using?
So it depends. It depends on the wavelength we actually want to generate. So in terms of 800 nanometer, we use a 405 nanometer laser. In terms of Telecom wavelength, we actually use a 532 nanometer pump laser.
Okay, very good. Annalena, please. Another question from your side.
Did you give the word to me? I'm sorry, there's some noisy...
Okay. I saw your hands, your hand, so
yes,
a mistake. Okay, so
no, it's not a mistake. I would have a question, please.
Okay. Sorry.
To Kevin. I just didn't hear if you called out if it was my turn. Thank you. Very interesting. And it's nice to also see a pure implementation of entanglement of QKD. The source that you're using, does it involve any cryostatics, or it's room temperature lasers?
It's room temperature. So that's the beauty of the concept. For the source itself, we don't need any kind of cryostat. That's another story for the detection. So there are different concepts. And if you think about the nanowire detection schemes, in this case, you have to have some kind of cryostat. But there are some opportunities as well to go into other detectors.
Okay, and the test for July, at what distances you are thinking to test?
I think it's 70 kilometers. So it's a link between two cities in Georgia. A real operational telecom network. Yeah.
Okay, so yeah, it's below the typical 100 at which the entanglement is fading away.
It depends, I would say. So we also have done some calculations on it, experience in the lab, going through, let's say, a real lossy link with 40 dBs. So it's for especially the satellite QKD we are also involved. And there we can generate 100 bits per second. So it really depends what you want to generate in terms of key rate. With one single source, 100 bit was also possible with 40 dB loss over the whole system. I'm not sure how this will connect to fibers. I think it's times 4 or 5 in this case. So you can go over 100 kilometer, depending on the key rate you want to achieve. That's for sure every time an issue, or let's say, has to be taken into account.
Okay, thank you.
Okay, so I don't see any other question from you, Kevin. So thank you again. Thank you very much for your nice presentation.
Thanks a lot.
And next speaker is Baptiste Gouault. He's a research engineer at iXblue Photonics. So Baptiste, the floor is yours. So you can share your screen with your presentation.
Yes. Can you see my screen?
Yeah, perfect.
Very nice.
Thank you.
So good afternoon, everybody, and thanks a lot to the EPIC team for organizing this meeting. I would first like to, a few comments on quantum communication ecosystem in Europe. So many things have been said today already, but so I completely agree. So we have a strong academic community in Europe. We also have a strong photonics industry, as we can all see today. And there is an increasing demand from governments and the European Union, and especially a demand for European and mature quantum communication systems, with a lot of work going on right now in Europe to make these systems. What are the requirements of quantum communications? So as you all know, you need performant hardware. So most of it will be similar to laser communications hardware, but the focus is a bit different, and the main focus is mastered noise properties. And as you have seen also, there is some hardware which will be very specific to quantum protocols, which might be single photons or single photon sources or detectors, or photon pair sources. You will usually need efficient signal processing, as you have heard with the Maxim presentation before. You will need to comply with cybersecurity standards, and there is still a lot of work to be done here. You might want your components and systems to be space qualified, and also linked to cybersecurity, you want a trusted supply chain. So now a few words about iXblue. So as you have guessed, iXblue is a French company with many sites, R&D and production all around France. And for photonics, the sites are in Besançon, Lannion, and Bordeaux. And in Bordeaux, you will find Kylian and Newcans, who joined iXblue last year. So iXblue Photonics has a large range of photonics products, from components to systems and instruments. And I will not comment on all of them, but comment on a few of them which are particularly relevant for quantum communications. So first, some words about the electro-optic modulators. So these modulators, you send some laser in and some electrical signal, and you end up with a modulated laser, which can be phase, amplitude, IQ, polarization modulated. This can be many wavelengths, and for quantum communications, you will want to focus on some signal quality parameters, such as the extinction ratio, insertion loss, if your modulator is in the quantum channel or maybe just before detection, or other signal quality parameters. So this is an example at the component level. Another example is at the subsystem level. So here I can tell you a bit about our micro-optical assemblies. So these are very compact and stable optical assemblies, which are usually free space assemblies. They are really optimized in terms of optical performances to your need. So during assembly, the optical performances are actually measured live, and all the components carefully aligned to optimize these performances. And then the components are glued, and the performance are kept stable over a large range of temperature, and then the package system can be sent into space. So a few examples of these assemblies are delay line interferometers. If you are doing DV QKD with phase encoding, you will probably use Telecom multiplexers to allow your quantum channel to live together with standard optical channels, say. You might use optical hybrids if you're into current schemes, such as CVQKD. And all the three pictures on the right here are an optical hybrid. But really, any custom optical layout, from the simple passive ones to much larger one, can be designed and built. And they can include active components such as optical shutters, AOMs, EOMs. And there, at the system level, so not discussed today are obviously the fiber optic gyroscopes. And here I just wanted to mention the spaceborne optical transceivers that we make together with Airbus. So including a lot of the components and subsystems from iXblue. And to finish, I would like to tell you a bit about the Open QKD consortium, in which iXblue is contributing as well. So this is a large consortium, European consortium coordinated by the Austrian Institute of Technology. In this consortium, a lot of use cases for QKD are tested all around Europe. There is a lot of work on standards with ETSI, as an example. All right, and iXblue has a more specific role in this project. We are working together with CNRS, also, as you've heard, on CVQKD systems. So we initiated this work as part of Open QKD, and we are expecting to accelerate these developments in the coming few years. So you've heard a lot already on the details of CVQKDs. It's mostly an optical current channel, but there the signal is hidden in the quantum detection noise. So with this, I would like to thank you, and I'm open for discussions and questions. Thanks a lot.
Thanks a lot, Baptiste. Thanks a lot. That's what's really nice what iXblue is doing, in all the quantum applications, but also in QKD now. We have one question, but before going to that, I would like to ask a question myself. So you bring at the very beginning the need that we have for mastering the noise in those systems. Can you please let me know which directions you're looking into the photonics community to help reducing this noise at levels, at levels that it's acceptable? Actually, we have a lot of people inside here that they might listen. They might be happy to listen what they have to offer for those next systems of quantum key distribution.
So one example, for example, something we don't make at iXblue is balance detectors and detectors in general. And when working on CVQKD, we have been investigating into using the most modern integrated detectors from the industry at tens of gigahertz bandwidth. And it appeared that the noise properties, and for example, the photon shot noise properties of these systems is actually quite complex and much different from the basic theory of quantum physics. So there, well, as for now, we just cannot explain this noise with basic quantum theory, and we have a lot to learn from the manufacturers themselves.
Oh, that's interesting. Huh?
So that's an example at the noise level. Then, then it's complete systems. So, well, you have to be very careful at every level of what can be the sources of noise and really control them everywhere. That's one of the challenges of QKD, and especially if you want QKD in the field rather than just in labs.
Okay, thanks a lot. Thanks a lot about this. And we have a question from Dylan McGuire from ANSYS, and maybe something he would like us to show us something. The floor is yours, Dylan.
That's great. Thanks, thanks, Paolo. So maybe first a question for Baptiste. You're showing some of the micro-optical assemblies. Do you see a pathway forward for more integration in the kind of photonic integrated circuits concepts, taking some of those components that you have and fabricating them on chip and delivering solutions that way? And from that perspective, where do you see some key challenges as well?
So the question is whether photonic integrated circuits, how do you make the compromise between choosing an integrated circuit or a free space circuit, I guess. Here at my level of understanding it, it's not so easy. In QKD, as I said, you really want to master the properties of your system. So at the level of system integrator, then you will actually compare both. You want to compare what you can do with existing systems, and then optimizing the performances. You will probably go to integrated circuits if you want something very compact. We heard before about having CVQKD system that fits in a SFP module. So this, in principle, would be nicer in integrated circuits, but as I said just before, we tried to use very integrated circuits, and for now we cannot explain their quantum physics noise properties. So for now, if you want to build a system that works right now, many of the components will be free space optics, and there is a lot of work going on much more integrated circuits, but so far it's hard to make them work, to make them compatible with QKD.
Well, that's really interesting. I think we have an opportunity here. Maybe if I just share my screen quickly.
Maybe I have to release the. Can I do this? I'm not sure how.
No, I think
that's good. That's good, Dylan.
You can see it from this side. That's great. So I think it's quite topical. I work for the ANSYS numerical team, and hopefully some of you are familiar with some of our photonic simulation tools, which have a pretty well-earned reputation for photonic simulation. And today, we have a lot of customers that are already using those tools to design and take these micro optics and bring them into integrated systems and kind of do some of the analysis that you've been talking with there in terms of some of the the challenges with making those processes repeatable and reliable. And I think what I wanted to introduce to this group today was a new tool that we've just started to roll out around actually taking the classical photonic simulation and bringing that into the quantum realm. And so we have now a tool called QInterconnect, which enables engineers and designers to simulate actually quantum state transformations in photonic integrated circuits. So, just as a really simple example, I think there's some great tools out there already where this is a nonlinear sine gate, you're making a transformation and introducing that nonlinearity using linear optics. And there's, good solutions to look at this from a diagrammatic perspective, but we can take something like this and turn it into an actual circuit representation. And this is again in the photonic integrated circuit sense. And we can simulate that using components that you would actually be able to fabricate in these integrated systems. So for example, you have your physical design of a beam splitter, directional coupler, and we can extract parameters from that either from simulation or actually from measurements. We have lots of foundry partners who are producing process design kits where you can actually go to that foundry partner, say, I want to design something. They have already qualified component models that you can build your integrated circuit around and evaluate it. And so what we've been able to do with this tool is actually add the capability now to run quantum states through these systems and account for real manufacturing imperfections. If you have, for example, mismatch in your S parameters for your beam splitter, your directional coupler. If you have loss in your system, we can translate the classic loss into a quantum compatible version that will maintain the unitarity of the system and calculate some of the behavior of your system now over a range of operating conditions given those input states. So this is something that I just wanted to share with the community, that's something that's available in our upcoming release. And in that pathway to go from the micro optics or these smaller scale systems and bring it into a photonic integrated circuit. Now we have tooling that will support the simulation both on the development of the classical components, but also now looking at it from a quantum information perspective.
Thanks a lot, Dinan. Thanks a lot. So that's a very interesting also tool that the PIX industry can use. So whoever wants to know a bit more can go back to Dylan. And since we have a question that comes from Amir. Hello, Amir. It's been some time.
Hello. Actually, this is a question to Dylan, and it's quite interesting. Actually, hello. Yes, actually. So you mentioned and already mentioned, as you said, you have like a circuit level nonlinear simulation capabilities. Can you simulate also like what kind of can you do SBDCs or other wavelengths conversion?
So maybe I'll just sort of share my screen again really quickly here. So in the diagram that I was showing here, this is an example of a nonlinear sine gate. So that the nonlinearity comes from the interaction that you get between some ancilla photons and the quantum state that you passed into this particular system. So it's implementing a nonlinearity in the quantum information sense using linear optical elements. Now with this tool and with a lot of our modeling tools, we can simulate nonlinear behaviors. So for example, we can model nonlinear fibers, nonlinear waveguides, and look at those characterizations. And I think one thing that's very important in this context is also being able to model the sources directly. And you mentioned the SBDCs. That's very near term on our roadmap in terms of having a model that, we can already do the classical nonlinearity in our modeling, but actually taking that result and turning it into a density matrix as an input into your quantum circuit. So from the classical parts, we already have the capabilities to do nonlinear waveguide modeling in both the physical models and the compact models. And we're in the process of also building that as an input into this quantum circuit simulation.
It's quite interesting. By any chance are you coming to Brussels for the PIC International? I would love to actually exchange with you.
Well, please reach out, and we can certainly talk further about some of the details of it. I don't know when the next time I'll be there personally, but if there's an opportunity, you never know.
Excellent.
Perfect. We can also connect you, Amir. We can connect you with Dylan here. I will do it. I note it. And I would like to go now to the next speaker, please. I will ask everybody to stay 5 more minutes after 5, so we can complete this meeting with the full talk of Vanessa Diaz from Lux Quanta. And Vanessa, the floor is yours. Be sure that you are not muted. We cannot hear you yet. Perfect. We can.
There we go. Okay, well, thank you very much. I'm thrilled to be here. I've been in the telecom industry for 20 years now, and I did this big jump into the quantum realm to work with Lux Quanta as a business development director, and I love it every time I get together with people like you guys. This is a really exciting market. So because I'm at the end of the day of the session, I thought that all the information about what we do in Lux Quanta, which is continuous variable QKD, had been already shared, which is the case. So I thought that best was to just walk you through who we are and what we do, and you just get the message on where we are, what we're planning to do, and whether we could potentially get together. So Lux Quanta was born in response to the market where cryptography, traditional cryptography, is just threatened, not only because this crazy story about the quantum computing that is real than never before, but also because anything that relies on mathematical problems might actually be hacked, potentially even today. So the whole world is now in a race to deliver this technology that is actually in the market for more than a decade now. But there is a big push from all these different regions in the world, Europe being one of them. So we've heard today about many projects that funded with by the European Commission were actually nurturing and empowering this market just to make sure that this region in the world is capable of manufacturing their own, not only at the QKD level, but also inside all the components level. So these are some of the projects where the members of Lux Quanta actually have been part of before we became a company. One of them, Civic, was in fact the one that gave birth to our first prototype, and that gave us the final green light to just become a company. So we are barely a year and a few days old only. We were born on May last year in a response to deliver or meet the demand of the QKD market across the entire world. So we're talking about $5 billion dollars across the entire world, 1.3 only in Europe. So we have right now 9 employees, but we're actually planning to double the number over the next half a year. We got really impressive investors as well from day one. Corning is actually the company that I come from, where I was for a decade working in market development. ICFO is basically our DNA because we were born in ICFO. For 4 years, all the technology was incubated until it was ready to see the world. And then we have also GTD. That's a very important software and system engineering company here in Spain. So this is actually what was born and made out of that last funds from the European Union and what actually became our first prototype. So we work with QKD technology. We've seen today an explanation about the 2 main different ones, leaving aside the entanglement version. So these are prepare and measure technologies. Discrete variable is the one that has been in the industry for a decade now, more than a decade. Continuous variable is the new kid on the block and is the one that is right now manufactured by a handful of companies across the entire world, and the solution that is actually promising to complement discrete variable. I never in my life in the commercial side of the story, I've never thought that one solution meets all problems. I think that there is a space actually for all these different solutions. Yet the value of continuous variable is because it's made, as explained before by Huawei and other members of today's talk, is made of components off the shelf from the telecom industry. So that what makes very doable, lowering the cost of these systems. So it's going to be an important push for the QKD market, what the QKD manufacturers can make in terms of cost, but also the ability of these systems to also coexist in existing networks. So that ability to have the quantum channel in the same optical fiber as I have the data, that's one of the big things that we can actually help with. The trade-off, like everything in life, is the distances. So you saw some of the numbers shared by Maxim earlier on. We're talking in our technology roughly about 30 kilometers, but it all depends on the characteristics of the channel and other variables. Overall, this technology not only has the potential to be very easy to integrate and also be a bit more cost effective, but also has a very clear path in terms of photonic integration. And that is going to make things not only small, but once again, it's going to make them even more competitive in price. So we are right now halfway in our development. So from the prototype that you saw before, we're actually on the pathway to commercialize this. So the message that we wanted to put out there is that we're ready. We're actually a team of people that, as I said, is growing. This is just the core team. The bulk of it is very strong R&D engineers and doctors. Actually, when I was hired, because I was one of the last ones to be hired in the team, and when I was actually checked, by the rest of the team, I was the only engineer, so I felt like Wolowitz from Big Bang Theory. It's a really cool team of people to work with, and I'm actually complementing them on the commercial side and getting new people on that side as well, because there is an awful lot of work to do. So our expertise, as you can imagine, in this type of products goes from the optical level, where of course all the quantum magic happens, up to the digital signal processing and system control at the FPGA level. And then the software, because the digital signal processing is what makes actually continuous variable QKD the heart of what it can actually make. The bulk of it is actually in the digital signal processing. So that's the message that we wanted to, just use to wrap up this little talk about who we are and what we do. I didn't tell you, we are actually based in Barcelona, the city of light. So we are searching for opportunities to actually test this technology in a real environment and different business cases, because again, it's not gonna, we believe that it is gonna have to meet different requirements depending on where it's going to be installed. So we actually believe that the time is now to start doing that exercise, and that's what we wanna be doing. So of course, I can also offer a visit to Barcelona. So I think that that's another boost. Thank you very much. You have there my business email, so feel free to contact me if you think we can get together again to test our solutions, but also to talk about partnerships at all the different levels that we cover. Thank you very much.
Thanks a lot, Vanessa. Thanks a lot for the invitation, for the nice presentation, for your energy and everything. And we have a question for you that comes from He Kang from NOIC.
Okay, so thank you for your presentation, Vanessa. So just one question. So what's the relationship between your company and the Q side?
Oh, that's a very good question. We both are born from ICFO, the Institute of Science. So ICFO has many different departments they have actually doctors from across the world researching in photonic sciences in many different angles. So when they actually think that an idea is really cool and fit for the market, they release it out there. And that's what they did with QSide 4 years ago. So right now, they are part of the components that we have in our system. So we often call them our sister company.
Okay, thank you. So just one more question. So if I remember correctly, the QRNG chip from QSide is based on indium phosphide materials. So what kind of photonic chip used by your product? Is still indium phosphide?
Well, that's actually the journey that we have ahead. Right now, what we're working is, as I like to say, at the macro level. So all the components are actually, you can touch them and assemble them together. But it's on the journey to just go into the photonic integration.
Okay, thank you. So if you're interested, you can contact me because we have silicon photonic chip for CVQKD.
Right. Excellent. Thank you very much.
Thank you very much.
Thanks a lot for the answer, Vanessa, and thanks a lot for the question also, Yang. And we have another question. No, I'm sorry. No, it's not a question.
No.
Do you have any other question for Vanessa? If not, Vanessa, I would like to thank you a lot for this nice presentation. I would like to thank all the speakers. And at this moment, I would like to share my screen. So everybody can see my screen. So what we discuss about today is that actually we are having there ready to be implemented. What we need further to qualify the system we're using. We need ways to find performant hardware.
I see a black screen. I don't know if it's me or.
I'm sorry?
I see a black screen.
I'm sorry, Panos, also your screen is not sharing. It might be your bandwidth.
Yeah, actually, I think I'm still on stage. Now I am more on stage.
You're muted, I'm sorry, and I cannot hear you either.
So I think
I'm back. I had some issues with my Zoom. I dropped out. It's very warm, I think, the room for the laptop. So I'm back. That's okay. We're a little bit out of time. I just want to thank everybody for being here today, for presenting their jobs, and all the people that actively participated. Amir helped me. Thanks a lot for helping me with this problem at the very end. And everybody has a nice evening. Thanks a lot.
Thank you. Take care, everybody.
Thanks, Panos. Thanks.
So for the rest of people that are still here